Homework 2.1, Basics of Functions, Video 2. Homework due Friday, May 22nd, 2020 at 11:59 p.m. In the previous video, we defined relation, domain, range, and function, and we answered 3 questions on 2 relations that were on the board. What's the domain? What's the range? What's the function? Or is it a function? The 2 relations we looked at, one was a list of ordered pairs, the other one was a table of values. But there's more than 2 ways to represent relations. A third way to represent a relation is with a graph. Now, I know we haven't really talked about graphing much, but there are some graphing basics that I expect you to already know. For example, on this picture here of this line segment, I expect you to know the coordinates of the left point and the right point. For example, this right point, to get to it from the origin, you go over 3 and up 4. So what would the coordinates of that point be? 3, 4. What would the coordinates of this point be? Well, the coordinates, the first one is the x, which is how far you travel horizontally along the x-axis. And the second coordinate is the y, which is how far you travel vertically parallel to the y-axis. So to get to this point from the origin, I would have to go back 2 and up 1. So -2, up 1. If you need some more review on graphing basics, let me know and I'll help you out. All right, so I've got 2 graphs up here. I've got this line segment from -2 to, -2, 1 to 3, 4. And I have this sideways U shape. You may know it as a parabola that kind of turns here back at 1, 7, and then going to the right ends at the point 8, 4 and 8, 10. And if you notice, I've got both of those circles empty, meaning that they're not actually part of the graph. They're serving as a boundary, but it's not actually there. So somebody remove those 2 points. Now, these graphs and all graphs do represent relations. Now, how do they do that? Because isn't a relation a set of ordered pairs? Well, yes, and even though these are graphs, graphs are relations. Graphs are relations. I'll show what's wrong with this marker. Graphs are relations because they imply ordered pairs. They imply ordered pairs. Meaning that every point on the graph has an ordered pair associated with it. For example, this point is -2, 1. This point is 3, 4. What's this point? Well, I didn't draw it super accurately, but if it were drawn perfectly, and maybe if I had a ruler, I could measure how far over and how far up it is. So I may not know what each ordered pair is, but I know each point has an ordered pair associated with it. And the same thing over here. Every point on here has an ordered pair associated with it. We may or may not know its exact coordinates, but we know that it represents an ordered pair. Now, how many points are on each of these graphs? Hint, there's more than 2 on here, and there's more than 3. How many points can I fit in here? Well, geometrically speaking, a point has 0 dimensions, so it has no width. That means I can fit as many of them on here as I want, an infinite number of points. That will be important in just a moment. Okay, so graphs are relations because they imply ordered pairs. Every point on the graph has an ordered pair associated with it, and vice versa. If there's an ordered pair that's associated with a point not on the graph, like 3, 1, then it doesn't belong to the relation. So it is a well-defined relation, even if we can't clearly identify the coordinates for every point on the graph. So we're going to answer the same questions we did before. If you have a graph, what's the domain, what's the range, and is it a function? Now, the domain and range are a little tricky at first, but once you see how to answer it, it's actually pretty easy. But you got to think about what I'm asking you. I'm asking you what's the domain. So I'm asking you what are all the first coordinates or all the x coordinates on this graph. Well, one of the domain elements, of course, is -2 because it's the first coordinate for this point's ordered pair. And one of the domain elements is 3 because it's the first coordinate for this point's ordered pair. But are those the only domain elements? For example, is 1 in the domain of this relation? That's like asking, is there a point on this graph where the first coordinate is 1? I think there is. If we go over 1, there's a point up here that's over 1. We don't know how far up it is, but if we're only talking domain, we don't care how far up it is. We just know that there's a point over here whose x-coordinate is 1. Is there a point on here whose x-coordinate is -1? Let's go back to -1. Yeah, there's a point above it. So there is a point on this graph whose x-coordinate is -1. We don't know its y-coordinate, but if we're talking about domain, it doesn't matter. So what are all the x-coordinates? If you're thinking -2, -1, 0, 1, 2, and 3, that's some of them. But how many points are on this line? An infinite number. The points on this line are densely packed, meaning if you pick any 2 points, you can always find another one in between, no matter how close they are. And you can repeat that forever. Because there's an infinite number of points on here and they're so densely packed, we can't possibly list all of the domain values in a row by opening up a set of braces and listing them. There's just too many of them. So how can we describe the domain if we can't list everything? Well, think of it this way. I'm going to go to the x-axis, the horizontal axis, and put a dot everywhere that value is in the domain. For example, -2 is in the domain, so I'll put a dot there. 3 is in the domain, so I'll put a dot there. In fact, anywhere in between, like right here, there's a point above it that has the correct x-coordinate. So the domain is every possible value between here. Now, if I sit here and try to label them individually, it's going to take me a while. But every point in between is part of the domain. This looks a lot like a shaded portion of a number line. Wait a minute, does it include the endpoints? It does. This point on the end is included because -2 is a first coordinate on a point on the graph. So we want to include that. Let's use a bracket. And this point on the end is also included. So we'll put a bracket there. And how do we describe a shaded in region on a number line? Using an interval. How far left does this go? -2. How far right does it go? 3. Everything in between is included. So the domain as an interval is bracket -2, 3. Because the leftmost x was -2, the rightmost x was 3, and every x in between is included on the graph. So we can describe the domain as an interval, not as a set of individually listed values. But what about the range? Well, the range is the set of y-coordinates, or second coordinates, so we could do the exact same thing, but from a y perspective. For example, this point's second coordinate is 1, so 1 is an element of the range. This point's second coordinate is 4, so 4 is an element of the range. But what about everything in between? For example, what about 3? Is 3 a y value on this graph? Well, yeah, if I go out here, then this point's y-coordinate is 3. I don't know what its x-coordinate is, but we're talking range, so I don't care. And using the exact same argument, every point between 1 and 4 on the y-axis is part of this graph's range. So if we were to fill them all in, and both 1 and 4 are included because the dots are filled in, then we would put a bracket. So what's the range? It's from the lowest y value to the highest y value. So the range is bracket 1, 4. What I've just done with this graph is called projecting onto the x and y axis. To project a graph onto the x-axis means to just flatten it down to the x-axis and it doesn't spill out to the sides. You just smush it straight down and where it lands is the domain. For the range, you project it onto the y-axis, which means that you collapse it onto the y-axis. Nothing moves up or down, it just moves inward. And this graph would land between 1 and 4. That would be the range. Before we answer the question, is it a function, let's try the domain and range over here. Now, you don't have to physically collapse this graph down to the x-axis or over to the y-axis to get the domain and range, because there's a much easier way to get it. if you have a connected graph. Connected means that you can draw it without picking up your writing utensil. And there are graphs that are made of disconnected pieces. Oops, getting a little ahead of myself. Here's the easiest way to pull the domain off of a connected graph. Domain is x's. On a graph, x's are left to right. So you ask yourself two questions. What is the leftmost point's x-coordinate? What is the rightmost point's x-coordinate? How far left does the graph go? How far right does it go? This point is the leftmost point on this graph. And what is its x-coordinate? 1. What is the rightmost point's x-coordinate? Well, first off, both of these points that are empty have the same x-coordinate, so both of them are over 8. They're technically not part of the graph. This graph has no rightmost point because you can get closer and closer to this empty spot without arriving there. So we can think of these points as boundaries. So the better question is, what's the rightmost boundary of the graph? The rightmost point on this graph is over here at 8. And because the graph is connected, every x value in between is represented above. So what's the domain on this one? 1 to 8. But here's where you gotta be careful. Try to make the squeaky marker sound. Is there actually a point on this graph whose x is 1? Sure, that one, I know it's there because I really make the dots solid. So the 1 is included, but is the 8 included? In other words, is there a point filled in on this graph whose x-coordinate is 8? No, because I wrote the empty circles. So what can we put on here to represent that the boundary is not included in the interval? A parentheses. So the domain is from 1 to 8, bracket on the 1, parentheses on the 8. And we can do the same thing with the range. But remember, range is y values, y's move up and down. So for the range, we want to think from bottom to top. For the domain, you want to think left to right. The lowest point on this graph was supposed to be this empty boundary point here of 8, 4. So the lowest point on that graph has a y value of 4. And the highest point on the graph has a y value of 10. Every point in between has a corresponding point on the graph. So we can shade in everything between 10 and 4. But which is included? The 10, the 4, both, or neither? Well, since the 4 came from a point that's empty, it's not included, parentheses. And since the 10 came from a point that's empty, it's not included, parentheses. So what's the range? 4 to 10 with parentheses on both. Excuse me. So if you have a connected graph, it's kind of easy to pull off the domain and range if you know where to look. To summarize, the domain is the leftmost x to the rightmost x, as long as everything in between is connected. Brackets or parentheses is necessary. Did I say range? I might have said range. Let me try that again. The domain is the leftmost point's x to the rightmost point's x, assuming it's connected in between. The range is the lowest point's y to the highest point's y, assuming everything in between is connected. So we only have one more thing to answer. Is it a function? It's really easy to answer unless you don't know the trick. Well, let's start by asking what makes it not a function. If there are two x's with the same y value, this one is not a function. How do I know? Because I can find two x's with the same y value. For example, let's go over here to 6. Now, I don't know what this point above 6 is. I don't know how high up it is. I just know it's 6 comma something. But if I keep going up higher, there's another one that is also 6 comma something. So what do I know about these 2 points? Their x is the same, 6, but their y's have to be different because they're different heights above the x-axis. So I have found evidence of 2 points that violate being a function. 2 points with the same x, but the different y values. That won't happen over here, because no matter where I stop, if I go up, I'm not going to find 2 points. So how can you look at a graph and answer the question, are you a function? By using something called the vertical line test. I'm not going to write it on the board because I'm afraid this video is already no longer than I wanted. but I'll explain what it is really quickly. Oh yeah, we're at the 15-minute mark. The vertical line test simply says, if you can cross a graph twice with the vertical line, it is not a function. Because you've located 2 points with the same x but different y's. And vice versa, if you can't cross a graph more than once with the vertical line, then it is a function. So cross twice, no dice. I just made that up. If you cross it twice, it's not a function, otherwise it is. So no over there, and yes over here. And by the way, I haven't listed homework questions yet, because the homework questions that ask you some of these things also ask you more things we haven't talked about yet. I'll try to make the next few videos shorter. These first two went way longer than I expected.